Hey there, so I'm very excited about today's lecture. In the previous two sections, we talked about the indefinite integral, and in this section, we're going to look at the definite integral and how it relates to area. So let's get started. Okay, section 7.3, area and the definite integral. So a little bit of background to motivate this, a little bit of a history lesson here. And this is the method of exhaustion. Okay, so to calculate areas of geometric figures with straight edges, like rectangles, squares, triangles, different types of polygons, we use specific formulas that are easy to prove. Okay, the straight edges make it really nice and convenient. However, finding areas for shapes with edges that are curving is not so easy. So we know now that a simple formula for the area of a circle is pi r squared. But we just assume this. Where did it actually come from? Okay, well, the Greek mathematician Archimedes derived this formula by using a technique called the method of exhaustion, where a circle is filled with a polygon with greater and greater number of sides. And so I included this figure below here to kind of demonstrate that. So this black circle here, at first it's filled up with a pentagon, or you could put the pentagon around the outside of the circle, and you could find the exact area of that pentagon. Or you could increase the number of sides of your polygon and then find the exact area of that polygon, or increase the number of sides again and again and again and again. And notice how the extra space that's left over between the circle and the polygon itself is like shrinking as we let the number of sides of the polygon increase. So the pentagon wasn't all that accurate, but as we do more and more and more sides for our polygon, it gets closer and closer and closer to the true area of the circle. Okay, we get approximations. And so as the number of sides of each polygon increases, the area of the polygon gets closer and closer to the true area of the circle. And so if this sounds like a limit to you, that's because it is. Okay, Archimedes was doing calculus, quotes, calculus, almost 2,000 years before it was formally developed by Isaac Newton and Gottfried Leibniz in the 17th century. Okay, so the method of exhaustion can also utilize a series of rectangles, for example, to approximate the area inside shapes with curved edges. And so I actually used Desmos to develop this right here. And so here's just an approximation. Here's just some circle that's graphed here, and we do a bunch of these rectangles splitting up in the circle. And if we just add up all of those, all of the areas of those rectangles, then we get a decent approximation for the circle. Now, if the more rectangles we do, the better. Okay, so that if these keep getting smaller and smaller and there's more and more of them, then it's a closer and closer approximation to the actual circle. And so this is the technique that we're going to be focusing on today. Okay, is rectangles rather than polygons. Okay, so let's take an example of this one here. Let's do the circle example. Let's consider the region bounded by the y-axis, the x-axis, and the graph of f of x equals the square root of 4 minus x squared. So I have that graphed below here, and we're going to approximate the area inside this little, and it turns out that this is a little quarter of a circle. Okay, so on the left-hand side here, here's the full area. So I just have it fully shaded in. Pretend that we didn't know what the area of a circle formula was. Okay, what we want to do is we want to break this up into rectangles and do approximations. And so we're going to do really crude approximations at first, and we're going to get better and better and better as we do it more. So for the first approximation, let's do part A here. Let's approximate the area of the region using two rectangles. And we're going to determine the height of the rectangles by the value of the function at the left endpoint. This is going to be an important thing to keep track of. So I have this picture here, and it's a good idea that if you're doing these types of problems and you don't have a picture, you should draw a picture because it helps us visualize this. So the way we want to think about it is we want to find out what is the area of each one of these rectangles. And when I say left endpoint function values, that means when we're dividing it up, so we're dividing this whole region right here, all the way from 0 to 2, we're dividing it into two evenly spaced widths. So that means it's going to be 1, we're going from 0 to 1, and then we're going from 1 to 2. So the actual width right there is 1. for both of those. Okay, and we're going to get more and more detail, and we're going to formalize this process a little bit later. Okay, so each one of those rectangles has a width of 1. Okay, and then the height of each of these rectangles is determined by the function. And if we're doing left endpoints, then that means if you're looking at this rectangle, the left endpoint is going to be the corner of the rectangle that touches the function on the left side. So this first rectangle touches the function up there at 2. We can see that pretty clearly. For the second rectangle, the left endpoint is going to be this corner right there. And it's a little bit harder to tell exactly what the function value is right there. But the nice thing is, if we plug in an x value of 1, then that's going to tell us the matching function value. And so I don't know what that is right now, but this is where our calculator is going to come into play. Okay, so here we go. I'm going to write this as the area equals, and I'm just going to go through and I'm going to use the area formula for rectangles. All rectangles are length times width. Okay, so the width of each one of these rectangles is just 1. So it's going to be 1 times, and then the left endpoint function values. So for the left endpoint function value of the first rectangle, I already know that that's up there at 2, but I'm going to write it as f of 0 because that's the x value that corresponds to the left endpoint up there. So I'm going to write this as 1 times f of 0. Okay, that would represent the area of the first rectangle. Okay, moving on to the second rectangle, the width down there is still 1. So that's width times, and the height is going to be f of, and then like I said, for left endpoint, we're choosing this 1 right there to correspond with that left endpoint of the rectangle. So that's f of 1. Okay, so then this is going to be 1 times, and for now, I'll do it pretty much showing all of the steps. All of these examples for this first problem, we're using this function here. So square root of 4 minus x squared. So that's going to be times the square root of 4 minus 0 squared. Plus, okay, the next one, 1 times square root of, because we're plugging in f of 1, 4 minus 1 squared. Okay, so a lot of times with these, you would just go ahead and use your calculator right from the beginning. But here I wanted to really show you, this is length times width for each of these rectangles. Okay, so 1 times this first one, so that's just the square root of 4. So that's just going to be 2. Okay, and then this one is 1 times the square root of, so 4 minus 1 squared, that's going to be square root 3. Okay, and I do want to get decimal approximations because we want to compare all of our different answers that we're going to get. So I'm going to type this in, 2 plus square root of 3. And I'll just use a few decimal places here. 3.732. All right. So that's approximating the area of that region using 2 rectangles with left endpoints. Okay, now I just want to ask a quick question. Do you think that this is a good approximation for the area of this little quarter circle right here? Okay, not so great. Okay, it's okay, but it's not so great. Do you think that this is an overestimate or an underestimate? Okay, and then so what you should be noticing is because this because these rectangles are protruding outside of the circle, there's all of this extra shaded space that's outside of the circle that we're including. So this should be considered an overestimate. There's too much here. So let's try a different version. In part B, we're going to repeat this using the right endpoint. Okay, definitely pay attention to that because there's going to be kind of flipping around with using both versions. Okay, and so I have here on the right-hand side, it's the same situation where we do 2 separate rectangles. And so again, if we're dividing up the interval from 0 to 2 into 2 separate rectangles, we have the width is 1 here, and the width is also 1 there. For left endpoint, we grab the left corners of the rectangles, but for right endpoints, we want to grab the right corner of the rectangle and stop once we reach the function value. So this time it would be grabbing the function value on the right-hand side right there. Okay, now I'm talking about two rectangles, but since this circle is coming down, what's the function value if I picked the right corner? Now that one looks a little bit strange, but yeah, there's a rectangle right there that's just like right flat on the ground, okay? So you don't even see it. So if we do the right endpoint on that function or on that rectangle, the function value at that right endpoint is down there at 0. So that's why you don't see another rectangle right there, okay? But that's technically what it would look like if we were using a right endpoint system. So let's do the same setup again. Area would be, and then each of those rectangles is just length times height or width times height, however you want to think about it. So again, they're both 1 each time. It's 1 times f of, and so for right endpoints, the first rectangle is evaluated at f of 1. Okay. Plus the second rectangle is width of 1 times the function value at the right endpoint, which, like I said, over there at 2, the function value at 2 is 0, and that's why this rectangle doesn't even look like it's there. So then this is 1 times the square root of 4 minus 1 squared plus 1 times the square root of 4 minus, and then plugging in 2 squared. And that's why that one is a 0. So here we go, we get the square root 3. And then 1 times this, that's 4 minus 4, square root of 4, all of that is 0. Okay, so this gives us just the square root of 3. So if I type that in, again, I want to type these in and get some decimal approximations to compare our answers visually. 1.732. Okay. So this is the correct answer if we are using the right endpoint method. Okay, just like if we're asked to find the area using the left endpoint method, that's the correct answer for that method. Okay, but both of these are not really very good for finding the true area. Okay, these are the correct answers for those methods, but then think about this one. Is this an underestimate or an overestimate? Okay, well, looking at the right endpoint values, notice that the rectangles end up being like completely under the function. And then this one, there's a lot of empty space. The rectangle didn't even have any height there. So since there's this empty space that wasn't considered, that's still inside our circle or like underneath our function right there, this one is the underestimate. Okay, so then what do you think? We've got an overestimate and an underestimate. How can we make this a little bit better? Okay, well, before even adding extra rectangles, which is definitely the way to make it better, let's try this again using the midpoint of each interval, okay, rather than the left endpoint or the right endpoint. So again, I have a drawing here that I generated using Desmos to help us out, but if you're doing this by hand, I highly recommend that you draw your own picture to help you out. So this time for the midpoint of each interval. So we're still doing 2 rectangles, so we still have that one rectangle has a width of 1, another rectangle also has a width of 1. But then instead of doing left or right endpoints, we're looking at the midpoint of each of those rectangles. So you would find like this 0.5 location, which is the middle of the first one, and then you would draw your rectangle like equal distances in both directions from that midpoint. Okay, and then same with the other midpoints, you would have to find out what is the midpoint between 1 and 2, and it's 1.5, and that is where the height of the rectangle would be. And then I would draw my rectangle off to the sides in each direction from that midpoint. Okay, so let's work this one out. Area is going to be, so still a width of 1 for each of them, but now we're evaluating the rectangles at a function value of 0.5 for the first one and 1.5 for the second one. Okay, so this is 1 times the square root of 4 minus 0.5 squared plus 1 times the square root of 4 minus 1.5 squared. And I'm just going to go ahead and type all of this in and get a decimal approximation. So square root of 4 minus 0.5 squared, and then plus square root of 4 minus 1.5 squared. And so my decimal my decimal approximation here is about 3.259. Okay, and I'm just going 3 decimal places on all of these. Okay, so for this one, this is actually a little bit better. Okay, it's higher than our underestimate and it's lower than our overestimate. Okay, so this one is better. There's less space that's on the outside that makes it an overestimate, and there's less space on the inside that would make it the underestimate. Okay, now it's still not perfect, but this one is definitely better. Okay, so in order to make this get even better, we would definitely want to see, like I was drawing on these pictures up here, more than just 2 rectangles. The more rectangles you do, the less underestimate or overestimate space you have. Okay, so I'll make a new video to pick up in part D, where we're going to try to redo this using 4 and then 8 rectangles and see what our answers start to look like.